Okay, so I first start with the definition of symmetric space. So this is actually there is many way to see the symmetric space. For example, in the viewpoint of algebraic Lie groups and also from the geometry and so on. So because the symmetric spaces have a lot of the structures and a lot of the approach to the symmetric spaces. But here I want to approach the symmetric space in the viewpoint of the geometry. Okay, so first, let's define the symmetric space. So symmetric space is actually the Riemannian manifold with a specific property. So that property is that the geodesic refraction. So here is a geodesic refraction at any point is on the isometry of X. So that means so what is a geometric refraction? You can think of the exponential map for a given Riemannian manifold. So then you can define a reflection, right? So in general, geodesic refraction is not the isometry. So, but the symmetric space requires that the geodesic refraction is actually the isometry of the manifold. Okay, so that means that for any X point, so there is an isometry Sx. So this is an isometry corresponding to the geodesic refraction. Okay, so it fixes the X and their differential at X is just a minus identity. So that is just the symmetric definition of the symmetric space. So it is simple, but it gives a lot of the corollary or the result. The first, the symmetric space is geodesically complete. So that means that each geodesics extends to infinity. Okay, so if you think of the geodesic defined on some open interval, then you can think of here X. You can think of the symmetry at here Y. So that means that you can extend the geodesic a little more and a little more. So and then you can see that the average geodesic extends infinity. And second, the symmetric space is a homogeneous space. That means that for any 2 points in X, so there is an isometry which maps to X to the X prime. So this is also easily follows from the definition of symmetric space. So because if you have 2 points X prime, the distinct 2 points, then you can think of the geodesic connecting them, and then the geodesic symmetry at the middle point of X prime, geodesic segment. So gives the map, the isometry, which map the X onto X prime. Okay, so that is that implies that the isometric group of the symmetric space acts on symmetric space transitively. So from these two facts, we can also define the isotropy group. So the isotropy group is the closed subgroup of stabilizing the point X. Okay, so this we will denote by K. And also the symmetric space is the homogeneous. So you can see that every the isotropy group is isomorphic, so independent of the chosen point X. And you can embed the isotropy group into the orthogonal group of the tangent space of X at X. So this map is called the isotropy representation. So you can see that this is a compact group, and also this is a crossover group. So K is compact because the K is a crossover group of compact regroup. And also there is a G equivalent diffeomorphism from the G quotient K to the symmetric space X via obvious mapping. So this one. Okay. So symmetric space can be obtained by the regroup by the quotient out from the certain compact regroup. Okay, so then here is the examples of the symmetric space. The simple examples are the Euclidean space and the sphere and the hyperbolic space. So which has a constant sectional curvature -1. So these are the very simple examples. And the second example is the example we are interested in. And also it gives the interesting property to you. So this is the set of the symmetric, positive, definite, the n by n matrix in the SLNR. So this space is actually the symmetric space. So we can see why this is a symmetric space. So first, you can know that, so this Pn, the set of symmetric, the positive definite matrix, is inside the set of the all symmetric matrices. But on the other hand, the set of the all symmetric spaces is a real vector space. Okay, so this is just that means the Pn is the open subset of real vector space. So then we can define our Riemannian metric as follows. So if you have for the two vectors v and w, so at the tangent space of X of the Pn, so this is the open subset of the symmetric space, and the symmetric space is a vector space. So you can think of the two vectors are the symmetric matrix. So then you can define like this. For the symmetric space W, that take a trace of Vx inverse Wx inverse. So then we will see that this metric turns Pn into symmetric space. Okay, so here the SL action on the Pn. So this is G is a SN R element, and A is a Pn. Okay, so then you can define the action of G on A by the G transpose. Then the G transpose is also the symmetric and the positive definite matrix. So we can easily see that this is in the Pn. So this defines SLNR action on Pn, and also this action is isometric with respect to the Riemannian metric defined here. So this can be easily checked. So like this, maybe you can later check this. This is just a linear algebra. And so this action is isometric, and also the Pn is the action is transitive, because the the symmetric positive definite matrix P is written as for some G in SLNR, IP is G transpose and G. So this means that P is a G action on the identity in P. So the SL action on the Pn is transitive. So Pn is a homogeneous space under the action of the SLNR. And you can also see what is the isometric group of in this setting. So let's take the identity point. So this is also symmetric. The identity is a symmetric positive definite matrix. So then its isotropic group is SONR because it satisfies this G transposes identity. Okay. Then we define some inversion, which corresponding to the geometric reflection in the definition of symmetric space. Okay, so let's define a inversion. So inversion at the identity is defined as a SIX X inverse. Okay? So this is the isometry at I. So because it fixed identity and also its differential is a minus identity. You can easily see that. Okay. So then even if we prove that, so there is the geometric reflection at identity. So this implies that every point has the geometric reflection. So because the acceleration on the Pn is the transitive. So we can conclude that the Pn is a isometric space with respect to the chosen the Riemannian metric. And also the Pn, the symmetric space, is diffeomorphic to the SNR, the quotient by the SOA. So this is isotropic. Okay, so now, so we want to explore more the geometric property of a symmetric space. So to see that, we need the Cartan the decomposition of real algebra of G. Okay. So here is the definition. So given a point X, then you can define an involution of G. Okay, regroup G. So G is isometric group. Okay. Group X. So defined by like this. So because the X square is identity, so that means that the sigma X is sigma X is square is identity on G. So we have an involution of G. So then, and also it fixes identity. So sigma X induces an involution of the real algebra of G, okay, zeta X. So this zeta X is an involution. So zeta X decompose the real algebra of G into plus minus one eigenspaces. Okay. So we first claim that the one eigenspace of zeta X is so real algebra of the isotropic. Okay. So to see that the first, so observe that for any K in isotropic group, so it commutes with the SX. Okay, so because two elements fix X and their differential is minus the differential of K. So that means that they are same. So the K, the isotropy group, is a subgroup of the fixed point of the set of the fixed points of the sigma x. And also conversely, the for the element in G in the connected component of fixed points of sigma, okay, sigma x here. So then the G preserve the fixed points of the xx, right? Okay, here is. So x is an isolated point because the geodesic reflection fixes the x and also the sx does not any point in some neighborhood of the x. So x is an isolated point of the set of the fixed point of sx. So G must fix x because the G is in connected component. Okay, so we conclude that this inclusion. Okay. So that means that so here, where is okay, here. So plus the eigenspace. So that means the fixed point of the set x is actually the real algebra of isotropic group K. Okay. So now we pay attention to the -1 eigenspace. So because we know that the +1 eigenspace is the real algebra of the isotropic group. Actually, just we set by P the -1 eigenspace of the zeta x, the involution zeta x. So this is a very canonical the complement of the K. So +1 eigenspace. So then we have decomposition of real algebra of G. So K drag sum the P. So +1 eigenspace drag sum the -1 eigenspace. So from this the definition, we can see that K if you take a bracket of the KK, then you obtain also K, and the KP is inside P, and the PP bracket of PP is in the K. Okay, so this is a very basic fact. And P. So we have, and now that we have a Cartan decomposition, then we can give some metric on P, okay, and then G. So consider the map. We have a natural map from G to X by G map. We map the G to the GX, so actually it's kind of the OB map. And then we observe that the pi inverse GX is a GK, and the differential of the G pi at E, so is identity. It gives a map from the real algebra of G to a tangent space of X at X. So this is a K invariant linear map. Okay, so this is satisfied this map. So you can easily prove this one from the definition. So that means that so here is a map, the differential of pi E, and also there is the adjoint K action on the K, and here, so differential of K, so action on the tangent space of X at X. Okay, so this action actually the commutes. And also the corner, you can think of the corner of the differential of pi e. And so as you know, the element of the isotropic group K fixed X. So that means that the corner of the differential of pi e is just K. Okay. So that means that the differential, if you restrict the differential of the pi at E to the P minus one eigenspace, then this map is an isomorphism because it has a, so they have the same dimension, and so the corner is K, and so on. And then we have a Riemannian metric, I mean the symmetric metric at the tangent space here. Then you can put back the metric to the P through this differential map. So then define an inner product Q on P by like this. So this is a very natural definition. So then Q is actually autojoint of K invariant. So this comes from this diagram, this commit diagram. So we have so this equality. This is also difficult. Okay, so now that we have the autojoint, the K invariant, the metric on P, right here. So we want to extend the metric to the whole real algebra G. So there is the possible because just to extend the Q to the K autojoint to K, the invariant metric on G by choosing the autojoint K invariant metric on K and declaring the K is the perpendicular to the P. Okay, so this extends. So we have the autojoint K, the invariant metric on real algebra of G. Then we can extend to the metric to the left invariant metric on G, real of G, which is also right K invariant. And also the submersion, so the map pi is Riemannian. So that means that if you restrict the differential of the pi to the hg, so this is actually the space from the P under the action of the left action of G. So then this is the isometric. So summarizing so far, then if you start with a symmetric space, then we have an involution sigma of regroup G, and also we have a left independent metric on G, which is also right invariant with respect to the fixed point of sigma. Actually, so here is inside K. Yeah, so third one. The next, okay, and next we will see that how the converse work. So that means that if you have a involution of the regroup G and with this kind of metric, then you can define a symmetric spaces. Okay, so how to construct the autojoint K invariant metric on P? Okay, so given a connected real regroup G and with an involution sigma of G, so this is comes from, so this story comes from just the real algebra. Okay, so because so far we see that the symmetric space, actually the geometry, the information gives some the pre-algebraic data, right? Here in this section, we convert we will see that the converse from the algebraic, the real algebraic, the data, we will construct some geometry the data. Okay, so then we can define a Killing form. Okay, so adjoint, so the big adjoint is as you know, the representation of G into the GL general linear group of real algebra G, and the small adjoint is the representation of real algebra G into endomorphism of G, like this. So okay, so here we can. So okay, so then if you given the regroup data, you can define a linear form, the symmetric bilinear form, so-called the Killing form, by this. So Killing form of Y and G is the trace of the adjoint Y composition adjoint G. Okay. So this is purely the algebraic definition. And from the Killing form, we can define the real algebra, the semi-simple real algebra. So we say that the real algebra is semi-simple if it's radical. Radical means that the maximal solvable idea is trivial. So, but it turns out that actually the maximal solvable idea is a kind of corner of the Killing form. Okay, so in the viewpoint, there's a theorem. The real algebra is semi-simple if and only if the Killing form of G is a non-degenerate. Okay, so yeah, I like the theorem. Actually, so there are the many equivalent conditions for a real algebra to be semi-simple, but I like the definition. Sometimes some people use this spec to define the semi-simple real algebra. Anyway, though, we have if you have a semi-simple real algebra, then you have some non-degenerate symmetric bilinear form, okay? So-called Killing form. Okay, so then what is the relation between the Killing form and the Cartan decomposition? Okay, so we already saw that if you have a symmetric space, then you can decompose the real algebra of G into plus minus eigenspace, right? So K and G. So we know that so D3. So then we can see that what is the relation between them. Okay, first, so from these three the property, you can prove that for any Y in K and G in P, so the variation of by the Killing form B, so B, Y, and G, then this is 0. So because if you have Y, so adjoint Y, so K maps K, right? Because and the P, okay, so P maps P, okay? So and the adjoint G, so G is in P, so then K is P, and P is K, okay? So if you think of the matrix form like this, so 0, 0, like one of this one, and this one is like this. Okay, so then their product is 0. Okay, so we have this equality. So we know that K is perpendicular to the P, with respect to Killing form. Okay, so that means that, so even if the space P is determined by the Cartan involution, so which comes from the Riemannian, the geometric symmetry at symmetric space, or symmetric space. So, but here we know that the space P also can be determined by Killing form. Okay, so if you have a regroup G, then you can see that what is the maximum compact group K. Then you can know that what is the real algebra of K. The isotropic group is. Then once you know that what is a small k, then you can find the cross eigenspace P by using the Killing form. Okay, so this is P is in other words, the P is totally determined by the algebraic data. So here, that is the important point here. Okay, and also this is a joint K invariant positive definite bilinear form on P. Okay, so, and also in general, you can define the joint K invariant Riemannian metric on G. So write this by using the inversion, the sigma. Okay, so that means that from Killing form, you can define the ordinary K invariant metric on real algebra of G. Okay, so that means that you can extend the metric to all, so everywhere. Then you can define the left invariant metric on G, regroup G. So which is also the ordinary K invariant. So then you can give a Riemannian metric on G quotient K. So, and also this is a symmetric space because it has an inversion at identity and the Riemannian metric. It has also Riemannian metric. Okay. Okay, so let's look at the SLNR case. So that means the PN case, right? So PN is the isometric space, symmetric space corresponding to SLNR. Okay, here so first so to know what is Cartan decomposition of SLNR, let's see the inversion first. Then the sigma I is SLNR. We know that it's SI. So write this. Okay. Okay, so SI is a G transpose the inverse. So because if you compute the SI P, then you can see that just follow the definition, and finally you obtain this one. So the inversion, the Cartan inversion of SLNR is this map. Okay. So then is a differential at I, then we have this one. Okay. So the first one against base K is this one. This is corresponding to the SON, the real algebra of SON, and P is this one. So because so this is minus eigenspace. And also you can also compute what is the Killing form. So Killing form is this one. And also you can define the metric, the joint K invariant metric on real algebra of SLR. Okay, this is what happens in SLR. Okay, so so now we will see the flag and rank and the root decomposition. So because symmetric space has a non-positive sectional curvature from the curvature formula. So what is the curvature formula? So if you have two vectors, the y and g in P, so actually this is the tangent space at a point of symmetric space. So with unit vectors, then their sectional curvature is like this. Okay, so that means that the sectional curvature of symmetric space has a non-positive, right? So, but sometimes it has a negative sectional curvature, but most of the symmetric space have a non-positive. I mean, it has also general sectional curvature. Okay, so from this, we want to explore the total geodesic submanifold of symmetric space. So with the zero sectional curvature. So that means the Euclidean space. So that means that some Euclidean space is embedded into isometrically embedded into symmetric space, right? So this Euclidean submanifold, total geodesic submanifold, is a very important rule, having the very important role in the study of the symmetric space. So to see that, we need actually the root decomposition. Okay, so first we define a maximal thread of symmetric space. This is just a complete total geodesic Euclidean submanifold of maximal dimension. Okay, and the dimension of the thread of X is called the rank of symmetric space. So because the symmetric space is homogeneous, right? So the rank is well defined. And also the symmetric space is homogeneous. So if you once you know what happens at a point, then you know what happens everywhere. Okay. Okay, and also we define the notion of the regular vectors, regular geodesic, and the singular geodesic. Okay, so F is a flat and the X0 is the point in flat. Then the geodesic gamma is called a regular if there is not other the flat containing the geodesic gamma. Okay, that means that there is only one maximum flat containing the geodesic gamma. So and otherwise we call it the singular geodesic. Okay, so singular geodesic means that if you have a geodesic, there is a flat which contains a gamma, and also there are another the flat containing gamma. Okay, so this is the version of the singular geodesic. Okay, so we can turn the geometric information, including geometric data, to the algebraic data. Actually, the maximal flat corresponding to the maximal abelian subalgebra of P. Okay. So for the capital A, upper A, so this is the image of the expression map of the G. So this is a maximal abelian, the subgroup of G. Then by using the exponential map from the G to X, then you can define the maximal flat F. So always you can write the F, maximal flat F is AX, okay, for some maximal flat, the abelian the group. group of G. Okay, so all the maximum subalgebra of P are conjugate to each other. So this is one fact. And also that means that if F and F prime are the two flats, so then, okay, so not contained. So contained in P. So then there is some K element of isometric group such that it maps F to F prime. So that means that the isometric group of symmetric space so acts on the space of the maximum flat, the transitively. Okay. And also the A is the abelian. So now that we will so look at the root decomposition. Okay. Okay, so then the adjoint A is also abelian. So because this is just a real homomorphism, so that means that the two elements of adjoint A commute. Okay. So we can diagonalize all elements of adjoint of A simultaneously, and that means that it has a common eigenspaces. So that is the root space decomposition like this. Okay, actually, so G lambda is G lambda is an eigen kind of the vector space. Okay, so the KH preserve the Y. Autoscaling. Okay. So, but so this is impossible because this is adjoint to A is arbitrary. Okay. So just you can think of this is eigen the common. So G lambda is common eigen vector space. Okay. So lambda means that depends on the adjoint of H. So its eigenvalue varies, right? So lambda is kind of the eigenvalue corresponding to the eigenspace. Okay. So we have the root space decomposition. Okay, so lambda is you can see that lambda is the homomorphism, I mean the linear map from the A to R, and also the lambda is this is actually the set of roots we call the lambda root. So root is the for root lambda its eigenvector space is non-empty. Okay, so so then from the curvature the formula actually from the root space decomposition we want to characterize the regular geodesic and the singular geodesic. So from the curvature the formula, if H a vector H in A is a singular, then there exists some Y in the some, so not in G not. So because here every vector of G naught commutes with H, so it has no information. So anyway, so there is a Y not in the G naught such that the HY, the real bracket of H and Y is vanishes. Okay, so this is the adjoint Y. Because if you think of the definition of the singular geodesic, so here is geodesic, here is maximum flat, and also there is another maximum flat, right? So this is Y. Okay, so here there's a maximum flat. So this is this F. So here there is another flat f prime. Okay, so this, if you read the f is ax, so that means that y is in a. So then there is another f prime. So which commit with the y. Okay, so you can think of this picture. So anyway, so then you can write the y as like this, because this vector is in here side. So then you can compute the alternate h. The y is like this. Okay. So this means that for some lambda, actually whenever the c lambda, y lambda is at 0, then it's lambda h, the value of lambda h must be 0. Okay. To have the alternate hy is 0. Okay, that means that if the h is singular, then the lambda h is 0, for some root lambda. Okay, so that gives us some characterization of a singular geodesy. Okay, so okay, now I think okay, so let's finish this one. Okay, so from this observation, we proved that the singular, the set of the all singular the elements of A is the actually the general set of roots. Okay, so this is actually the general set of roots. So the lambda is actually the linear map from the A to R. So this gives us some hyper the plane in the A. Okay, and also the regular the space. I mean regular vectors. So that is the set of non-zero, the set of the roots, all roots. Okay. Okay, so then if you have the linear independent roots lambda 1, lambda s, then you can intersect the hyperplanes corresponding to each root. Then it gives a singular space of codimension S. Okay, and also if you have a conversely, if you have a okay, so that means that if you have the singular subspace P of codimension S, so the P is written as the intersection of the S, the maximal flats. Okay. And we say that singular subspace of dimension 1 is a maximal the singular elements, and also the connected components of A, the complement of the set of the singular singular vectors in A are called the Weierchamber of A. So because the A is a Euclidean, actually the Euclidean space, and the set of the singular the points and singular vectors is actually the union of some hyperplane. So like this. So then you have some connected components here. Okay. So these are called bichambers. Okay. And also the A plus, the fixed one, the bichamber. So A plus, it's just a fixed bichamber A plus. Then you can define the positive root. So which consists of the roots with the positive the value on the chosen the Weierchamber. Okay. And also the definer, we can find the basis, the delta of the set of the positive roots, and the set of in the delta is called the simple root. And also the cardinality of the delta equals to the rank of the symmetric space. I mean the dimension of A. And the zero set of the simple roots, the bound the chosen the bichamber, I mean the positive the bichamber. Okay. And also, so there are some structure on the singular space. Okay, so now I finished my first lecture here, and next I will give the examples of the root space decomposition, and what is a positive root and the simple root, and how looks like the bichamber, so and so on. Okay, so I stop here.